nutshell. So the word networks are at the heart of complex systems is kinds of a reality, and in fact, we will possibly will not be able to understand the complex system unless you develop understanding on the network science. So although it could be very aggressive statement, you can feel that it's very aggressive statement, but if you just open the literature, you can see that civil engineers are working with networks, mechanical engineers are working with networks, robotics, they work with networks, because networks can better model the whole complex system in terms of very basic building blocks like nodes and links. So the structure you get from a network, from a complex systems to a network, which could be, which fundamentals, laws and principle could be very common, right? So I can have a network built for a civil engineering system or transactions in a banking systems. They could have a very basic structure of graphs. There are nodes, there are links, and then that graph can show some structural property which may help us to develop or understand the whole system. So look into this picture. So here are I plot three. So these pictures are collected from majorly from, some of the pictures are taken from the Paravasi books on network science. So he is a pioneer on this network science. So this is from that book only, this picture. So three network, just look into that. The first network is a computer network. The second is a movie, a co-actor network. So in the movie, someone, Al Pacino, worked with Marlon Brando, and then their link is created. And the third picture is for a metabolic reaction of proteins network. Now, in a nutshell, all these three becomes a graph in the fourth picture. Now, if I have that graph, I may ask, whose degree is much higher? Who forms a triangle? So these kinds of questions I can ask, and the meaning of those answers will be different for different network, because co-actorship network, it will be, if a triangle is forming, that possibly they are appearing very frequently, they are in the same movie they are appearing. On the other hand, if that is happening in a disease network, it could be like that these 2 or 3 proteins causing several disease in a human life. Okay, so this is how the network or graph comes into picture. Now the question is, when network science, the origin of network science. So network science is very much very new discipline in of the 21st century, and it's become trends in this the first 2 decades of. So it starts with we'd say that in the 2002, 2003, 2004. So they pick up the papers in the research area, is heavily picked up this particular topic to solve different problems or different algorithms development. But the question is that why this origin is only 21st century, right? Because if I go to the metabolic reaction on that network, it's like origin of life. It's starting from there. Then the social network is as old as the humanity. Like you and me have formed the society, villages, cities. Everything is there for as old as you can think of. And even the graph theory, which is used for analyzing these networks, is as old as at least 200 years back. So the question is, why didn't we have a network science 200 years earlier? The answer is has a two major reasons. The first is the emergence of network data. Now comes the data into picture. Now to describe these kinds of complex system, let's say we want to describe how India fight against COVID and how people are connected or how the spread of this disease happens in India, we need a whole data of connections. How I talk with my students, whether that is over the phone or I am having a physical class here, or something is happening physically or not, whether distance of recommended distance is maintained or not, whether I am having mask or not. So these are data, right? And that data needs to be collected. Collecting data from these billions of users was difficult. Was difficult. Earlier, it used to have like a question answer. The researcher personally visit their home or their office and ask questions. Whom you like, whom you don't like, whom you called as a friend, whom you call not a friend. Now the question is, if I have a Facebook, I can see that there are many people that posting like in my many post. There are many people who are friends of me. In the Twitter, I am following someone. So that is clear with this data. Now this data is actually giving the boost that network science or network algorithm development is required. So in social network, we need who is a friend to whom. We can easily get it from Facebook, Twitter, like different systems. Although they preserve this data, they don't allow you to crawl the data, but at least they can have the data and do the analysis. And that is what they are doing. These giant companies are doing exactly the same thing. So they have all the data and they are doing their analysis. And those analyses are majorly network science analysis. And in case of World Wide Web, then you have a page, web page, which page is linked to whom, which other pages. And that network is actually kind of available for crawling. So if you can crawl, although the size of the network is very high, so if you can crawl that links. That is publicly available. Then the biological cell, now you need to do research with, earlier it used to have, always it used to have a very long lengthy process. Now the process are minimized with the availability of technology. So this is a process that boosts this network science analysis or research highly. So in the past, we lacked the tools to map these networks. That's a major cause. And another cause is it was difficult to preserve that also. So preserving that in the form, digital form was not possible that time. So memory was costlier. Then there was a very hard to share. The internet speed was only 28 kbps in 2000 or before that. So how you share the data from one place to another place? It was difficult to share. How you store? There was no cloud storage kinds of concept that time. Getting 1 GB data storage was very difficult. Now you can have a TV space only by paying $10 a month in a cloud. So now you can efficiently, effectively pass the data, share the data. There are methods, there are protocols by which, like JSON format, XML format, you share the data. You have a standardized, those protocols are standardized. Then you have the internet, fast internet. Right now I am sitting with a 1 Gbps line connected with my laptop. So that was not there earlier. So I can share that data. Even streaming these kinds of video was very difficult in early before 2000. And the cheap digital storage, you can have any sort of storage with a very less number of less price. And the second is the acceptability of network science as a universality of complex system representations. So the key discovery of network science is that the architecture of networks emerging in various domains, science, engineering, technology, medicine, and any even civil, any other things, other parts, management, they are actually forming a network. And that network, if you analyze, in the same analysis can give you the meaning of your problem. So this changes a lot of things in the understanding of the systems and how you use the network science for solving those problems. So this provides some mathematical tools which is common to all, and you can give your analysis dimension from one space. You can analyze the same manner. You can analyze different problems. Now, network science is a interdisciplinary science, interdisciplinary problem solving area where we talked about graph is the base, but based on top of that graph, you can have the problem you can address in any discipline, from any discipline like mathematics, like sociological aspects you can analyze. You can analyze management aspect. You can do system analysis, healthcare, medicine, everything you can do. The another important part is that network science is empirical. So it's not like a traditional graph theory where you are bothering about the traveling salesman problem. Yes, traveling salesman problem has its own benefit here also. But we are not concentrated only on a very traditional traveling salesman problems or vertex cover problems whose inference into the problem domains. There may be, but the researchers is not bothering about the inference of the practical users. But when I am talking about network science, any problems we will do, we'll have to empirically study a practical problems and real life network. And then in that real life network, we have to show that yes, this is the inference from that. Whether it's a viral marketing, whether it's a community where we're thinking, and whether it's a drug design, anything. So it's an empirical study, very closely. It's applied. You can say the applied graph theory. You can say that it's more of applications and how we perceive the social systems. So it's another name is social network analysis. So it talks about social systems. So what is the societal impact? We have economic impact, like we analyze, we have this PageRank comes into network science. So it's like how you search in the web, and then social networks, how you connect with your friends or peers. Then it's from healthcare. You can have a drug design, metabolic engineering. Now the question is, how come this vaccine, COVID vaccine comes so fast? Because we have simulated many things in computer, right? Computing helped that very quickly develop. Within 1 year, vaccine came into picture. But there are history where said that 400 years we don't have any vaccine for a particular disease. But now we can come up with a vaccine within 1 year, not even one vaccine. We come up with like 4 or 5 different variants of vaccine of COVID. And this data analysis actually helped, right? Now that data analysis, obviously we talked about genes, DNA, how they are reacting, RNA, how they are reacting, those forms a network. And possibly network science has a very good role, at least in healthcare drug design. Then security, we want to fight against terrorism. There are criminal network studies, how you identify criminal out of just tweets. There are criminals use public forums like Twitter or any other public forum where to communicate with each other. Can we identify that? Then we can have something like fake news identification, or how can you stop that? Then epidemics. This is definitely, I personally worked with this contact tracing applications for my institute. So here this contact tracing is coming from a mobile applications was developed like Go Corona Go by IISc. We are using that Go Corona Go applications, and that contact graph giving us some insights that where their people are gathering more, where we need to keep eye on, and these things are provided by these kinds of social network analysis. Then neuroscience, mapping the brains and other things that will come into picture. Management, uncovering the internal structure of an organization, who talks to whom, kinds of things. So, any questions? So whenever you have some question, you can stop me and ask the question. I will be happy to answer. So now network is only very basic elements are nodes and links. And if I talk about nodes and links, one thing's coming to picture, whether it's a graph or network. Why you are saying network? It's just a graph. So in this particular development, we actually we are actually interchangeably use network and graph. One is that the common terms are here that in graph theory we talk called vertex, here we call node. In graph theory called edge, here we call link. But in anything you can use and that is correct. It's not like you cannot use that. So let me just share one Jupyter notebook and show you how now we can have network formed. So I personally use NetworkX for my research purpose or in algorithm development. I use Python and NetworkX for network analysis, but there are ample amount of softwares or libraries available for in network analysis. So you can have iGraph. iGraph is available for R language as well as Python. Then there is this Stanford Network Analysis Group have C++ package, which is also available in Python via wrapper library. So this line is important in importing NetworkX, and if we want to create a network, just we can add edges. So if I add edge, and then we can have a network like this. Now, there are some benchmark data available with that, and that one of that is Jackary's Karate Club. So I just give you that if you have a graph loaded, then you can just have the information of that graph can be using that index.info, pass the graph, and you get the number of nodes, number of edges, and what is the average degree. You'll have that in you. Quickly you can view what is the network. Now, Jackary's Karate Club is a study happens in 1970s, and this is a very important graph because it shows community structure, and there are only 34 nodes, a very small graph, 34 nodes, but in reality it happens that this is a karate club, and eventually that karate club broke into two, and here you can see that there is definitely one half around 0 and another is around 34 or 33. So these two are, one is instructor and one is a club owner. So based on that, this club was broke in that time. So it's a very important benchmark graph. Similarly, we have Southern Oman dataset, where the network is formed. These are the traditional networks. Okay, these networks are formed by the questionnaire or survey. So this survey was conducted between between two women, if they attended the same party or not, and then there is a link, whether they talked in that party or not, something like that. Now, where do you find the network? So this is a page of Stanford, and this group is called SNAP, Stanford Network Analysis Project. So here you can find several data sets, network data sets. If I go there, I can see that there are social networks. So these are social networks like Facebook, G+, Twitter, Opinions, Live Journals. And then there are like community where ground truth community levels are available. So you want to study some community detection algorithms, you can do that here. Then communication network, email communication, telephonic communications, wiki talks, citation network. So we have this bibliographic data because this is mostly attended by faculties. So they knows that papers we have citations, and then that with those citations we can build up a network where nodes will be papers and the links will be citations. So this citation networks available, collaboration networks available where two person is collaborating with each other. Maybe that is a co-author, maybe that is a something else like co-actors. Then web graph, product purchasing network, then road network. So those are available. So in my presentations I loaded one. So I directly loaded from some other sources. It's a football network. Now interestingly, this is like a football schedule network. So if I have this, so I can create a football network. And see, I am showing you a very small network because visualizing the high, means large scale networks is very difficult. Now what I also did is like, if I can open Twitter and have some tweets. Okay. So if I have some tweets and I want to build networks, how could I do that network building? Here from here, the tweets is a just simple text, right? It's a text. Some text is there. So how could I just build a network? See, each tweets have some mentions. So this particular person mentioned this. So I can build that network. I can build the connections from there. Similarly, these tweets have many hashtags. So I can build that these hashtags are two hashtags are coming together. So this way I can build a network. So I have created some links with hashtag, some hashtags I have created like COVID during that time. So I have. So if you have five, six tweets, and then you can create the links from there, and you can build a data set like this way. That one is your source, and another one is your destination, and then you can load that into your notebook simply by a pandas package. So pandas will give you a age list, something like this. So this age list, you can convert that into a network by network package. There is a option or functions called from pandas age list. And that gives me this kinds of network. Then we have a degree distributions. We can have these degree distributions. That it's like a histogram. You draw a histogram, and that function is there. Usually, what we do is a log-log plot. We don't bother about normal. We do a log-log plot, which looks like something like this in a social network. And this kinds of distribution is called power law distributions, and that power law distribution is one of the property that many network shows in their nutshell. So, and if I generate a random network, and draw the degree distribution, so that comes like this. So it's not power law, right? But here it's power law in the first pictures. Here it's like something like Poisson distributions or so, or maybe binomial distributions. So going back to my presentation again. So the theory of random network model. Now, what is random network model? So apparently, when we see, when we saw one network or a graph, what we practically what we are doing is basically that we try to figure out how these links were built, right? So random network theory talks about that it's a random, completely random. So edges are coming randomly. So that is the very basic assumptions from where this random network model comes into picture. And what we do here is we create a number of nodes, fix the number of nodes, and create the link. But challenge is how to create that link, and we either it could be from any distributions or it could be just simply uniformly randomly select two nodes and put the links. So there are two major definitions of how we can build a random network. One is like graph, where we'll generate a graph by passing the number of nodes and number of links. So we pass the number of nodes I required, and then we pass the number of links what we required, and then we generate connect these links to the nodes. This was the model uh, uh, proposed by Herodes Reddy, and they are the pioneer on this random network study, and they have published like 8 papers or so during 1959 to 1968. And they studied this random network analysis, analyze those networks, how they form and other things. And the another model is where you generate a graph by stating the probability of link. So you pick two nodes and you generate a probability, and if it is greater than p, then you will generate the link, otherwise you will not generate the link. So this model was proposed by Gilbert in 1959. Independently, these two works actually started very same year. The publications happened in same year independently, and those are two models we still follow. So if you just go back, if I just go back to this, and this actually, although it's I am saying that it is any graph, but in the behind it is actually using NP model. So P is a probability here. See the definition, probability of execution. So it's a probability here. So I am basically using the second model for generating my graph. So how it works? It works a simple algorithm, 5 steps. Start with n isolated nodes, select a node pair, generate a random numbers between 0 to 1. And if it exists p, that is a probability, you connect that selected nodes, and you repeat that for all the node pairs in the network. So it will be in situ number of pairs. So for every node pairs you will generate. And what is the benefit of this model particularly? That links are not fixed priorly. The other model, you have to fix your links priorly. So here it's not fixed. So, so it gives you a kind of a window that you can have a different kinds of network with a different number of links. So here is one examples of the random network. See the first row, it's having p equals to 1 by 6. That is the probability, and the 12 is the number of nodes. But because this probability is used, that the number of links are different in the 3 graph. And the latter, it's a bottom row is like probability of 0.03 and n equals to 100. And there are many nodes which do not have any degree. So those are here. So they don't have any degree. So means they don't have any connections with the other part of the network. So usually this random network shows Poisson distributions or binomial distributions or intersection of that distributions. So means like average degree is like this picture. But if you talk about real networks are not Poisson distributed. So if you just look into this picture, the purple dots are the real networks distributions, and the green line is the distribution of the Poisson. of three different networks. And you can see the clear differences between these two particular distributions. If I go back to what we are showing, that here also this network is generated by the Barabasi-Albert model. So I generated this network Barabasi-Albert model with 1000 nodes, and the same 1000 node used here for Herodes Renyi network. But you can see the distribution is a very distinct and different distribution is there. So one property that social network shows is the property of small one. It's actually have a history, and that history comes from Milligram's famous experiment of 6 degrees of separation, where he targeted two users from Boston and Massachusetts, and then he select random people from other two cities and ask them to forward this letter to someone they knows by first name, and think that he is more close to that target person. So now each person did that, and it was repeated for 296 letters. Only 64 reaches to the destinations. Other lost, because that time it was not like that. These kinds of WhatsApp you can just search and ask. So many lost, but there is a 64 reach to the destinations, and when they did an analysis of average number of hops they traveled, it comes to a 6 was the average. And then this term comes into picture, that 6 degrees of separation. So the left picture here is that distribution of that 64 letters, and you can see that the average is around 5 and 6. And the right side picture is a Facebook study where the same kinds of experiment happens with the available Facebook network, and the number comes around 4. You can see the picture in the right graph. It's around 4 where it converges. And then you know the number of, in that time, the same time frame, you know the number of nodes, and you know the number of links in the network, and you can also have a mathematical study. And that mathematical predictions was that time gave like 3.90. So the actual networks was 4, and the predicted value was 3.9, which was very close. But the question is that this n is not very small. Maybe in the Milligram's experiment, the link number of cases or links were very small number of only 296 out of that 64. Whether that needs to be considered or not, that is also a debatable question, right? That out of 296, only 64, it's like 33%, 30% or so. But here now with a very large scale network, still you can reach to other part of the network only by 4 degrees or 4 hop distance. That's an interesting property of a social network, and it comes from the hub structures. So there are many hubs in the network. So random networks are far from the real world networks, right? Now two questions comes here. One, why do so different systems like a worldwide network, or like a biological network, or a social network, or a LinkedIn professional network as compared to the Twitter network or the Facebook networks, converge to a similar scale-free architecture? Scale-free means this architecture where you have a power law distribution. Power law distributions in a nutshell is saying that you may have very high number of low degree nodes, but very small number of high degree nodes. That is coming there. So why is so? And the second question is, why does the random network model fails? Why random networks is not able to capture these things? To answer this Parabasi did this experiment, and they identified that Both of these questions can be answered by once two properties. One is growth and another one is preferential attachment. These two are important factors for analyzing any social networks or similar kinds of network where many networks, almost I would say almost 80% network will show these kinds of properties. And what is growth? That not all nodes comes in the same. So what is the assumptions in random network? Random network model assume that they all n nodes come simultaneously. Now the problem is to build the edge, but in actual network it's not true, right? In 2004 when Facebook started or 2002 something else started, that time what happened that some nodes were there. Then people onboarded with time. And when a people is onboarding, then there is a concept of preferential attachment, that there are already some nodes are there. They will be considered many times, right? So if I say t equals to 1, there are 10 nodes. Now t equals to 100, there may be 100 more nodes, but that 10 nodes is accessible to all these nodes, but not this first node will have the same access to the 100 t100 node, right? So that preferential attachment says that when once a new nodes appears into the system, they choose, they tend to connect with the higher degree node. So who are higher, they will try to connect to them. It's like if you today, if you create a Twitter account, you will first go and possibly will connect with Virat Kohli, or will connect with some like Shah Rukh Khan or Salman Khan or someone. So they are already having links. Rather, you will hardly search for a person who is also having a like link one or two. So that way, it's like a preferential attachment. You prefer who are already connected. So that's how it creates a hub-like structure. And this is what Barabasi-Albert network model works. So it says that it will have any node will come. So if you just look into this first T0, T1, T2, T3, T4, T5, T6, and so on. So each node comes into the network and having two fixed number of links, and that links is select by probability that who already have the links. In that probability they connect. So if it comes two links is there and both of them connected with the higher degree nodes in that, so the probability of connecting with them is higher. And exactly this algorithms is used where if I just go back to my code, so I use 1000 is my node, so the end result will be 1000, but that three fixed links they will create, but still that is creating a scale-free network. So some of the research area in this particular problem, one is network science, one is structural analysis. He wants to have some structure identified, like what are the cliques, the codes, clans, if there is some kinds of structure, whether that is having some balance or not in a sign network or not, it's having a bipartite natures or not. Then community rejection problem. So here you will try to understand what are the closely connected groups in the network. Then information diffusion means if I give information to some node, how that information diffuse throughout the network, how COVID is spreading in the network, how epidemic spread in the network, how we can stop that network, stop that spread. And then link prediction problems where you say that you may know this person, right? You always saw that in the Facebook or Twitter, you may know this person. So that is a link prediction problem. That algorithm basically in background working on a link prediction problem that you may also have a link with this particular person. And then there are temporal networks, like networks evolve with time, how will operate on that, those kinds of networks and so on. Centrality, an important factor in structural analysis that actually gives you the how a node score is, what is the node score. And some of there are many centrality measures, some of them are like the degree centrality, how many nodes you are connected with. Then between the centrality, how many shortest path going through you. And then there is this community rejection problems. You are bothering about how you can find that closely connected groups and whether at all the closely connected groups are there in that network or not. If there is, then what is the size of that community? Then information cascade I already told. So that's closes my first part. And if you have any questions, you can ask now, or you can have that in the question answer session.
Participant, you can mute yourself and can ask questions. You can unmute yourself and can ask questions.
So going to the second part of this presentation, where I will present what we have developed in our. So basically, most of these work are before coming to IIT Jodhpur, during my PhD and postdoctoral work. So I'll start with a total influence and hybrid simulations of independent cascade model using graph knowledge grammars published in 2020. So we start with information diffusion. So how information diffusion happens in the network. So if I give there some information to one of the nodes, let's say me, and what will be that reach, or how far that can be reached? That is the information diffusion problems. It has two parts. One is how the diffusion happens. That is a modeling of diffusion process itself. And it's a well studied. It's like from actively studied in online social network from 2002 onwards. And there are two models that is very popular. One of them is independent cascade model. So this independent cascade models is a stochastic methods in which flow of information depends on the neighbor probability of the link. So what happens that once I receive an information, so that information propagates to my neighbor by the probability we have the acceptance of that probability is in a real network is a very small, like 0.01 probability of getting that information from one person to network. So if you just roughly calculate, if I have 1,000 followers in my networks, only maybe 10% gets influence. So if I share something, only 10 reshare happens. So that is the probability of influence, my influence. There could be many likes, right? But once people reshares, that means it's an influence. They influence, that's why they share that to their network. You can also discuss some of the outliers who shared everything. That's a different issue. So how diffusion happens in this process? This process says that in T0, some information, some are like information contents are there, and then each step they will try to influence one of its neighbor. So if someone comes to my office, I will try to influence. Okay, let's have a coffee. So if I like coffee, I'll say you have to have coffee. Or if I like green tea, I'll say, hey, you should have a green tea every day 3 times, right? So that's my approach to influence someone. But whether he will be influenced or he or she will be influenced, that depends upon the probability that he or she trusts me or like or correlates with me. So that's the probability. We call it like diffusion probability, propagation probability, anything. I mean, those two terms are independently used interchangeably in different papers. But the question is that you are not able to there is this restriction in independent cascade model that I'll not, if he or she is not influenced, I'll not do this repeat same process later. So I'll not try to influence him or her after I tried once. But there is no deterministic approach available till date to measure the spread size. So if I give, let's say 10, I select 10% in the network and give some informations, how to measure the real spread is not available. What is available is that you have to do a stochastic simulation. And you know the stochastic simulations, you run once, it may come 10, you run twice, it may come 100, you run thrice, that may come 1000. So unless you repeat stochastic simulation many a times, your car will not be smooth. So if you create a prediction car, that will be variance will be very high. So you need to repeat like 10,000 times that simulations. Repeating 10,000 times a stochastic simulation for a network with even 4 lakhs, 5 lakhs, 1 million nodes is very tedious process. So it's a very time consuming process. A complementary research problems where you will find many papers is called influence maximization problems, where it says which seed nodes you have to identify, means you have to select to spread highest rate in the network. So it's a optimization problem, maximization problems where you need to select by a constant k. You will have only k numbers of nodes or seeds you can select, and then that k numbers which information flows. So this optimization problems is an NP-hard problem. It already proved in the literature. One of the solution is like greedy solution. So you do like this. You pick one test with these 10,000 Monte Carlo simulations. Then you pick another one, you test it in 10,000 Monte Carlo simulations. And so once you've done that, then you select the best one. That is your first seed. And you repeat that for k many times. And this is called the greedy solution. So it will be the optimized one, highest possible optimized result you will get. But see, for selecting k nodes, you have to calculate k times n into 10,000 simulations, almost n into 10,000 simulations. Considering n is much larger than k. So it's a very large number of simulations happening, and that simulation is very costly also. So we proposed a hybrid simulation of these independent cascade models, where we will be using RAF knowledge granule. So we'll use RAF set, concept of RAF sets, and we'll build a granules, and then we'll see how this model works. The objective is to reduce the number of times 10,000 or the time of these executions. There could be two approaches. In the literature, there are few approaches where they try to figure out to reduce the number from 10,000 to some lower number, guaranteeing the same number of accuracy. And here our objective was to reduce the execution time of each. So the total 10,000 times runs you can use and get the marginal, means get the marginal gain quickly. So this is how our algorithms work. Once I have a social network, I want to simulate, let's say, k seed nodes. So I first try to figure out the granules, the rough granules around all these k nodes. So who belongs to that granules? These granules belongs that basically identify two set of nodes. One is which is lower bound, that is only influenced by particular nodes. Let's look into this, the orange nodes here, who are actually influenced by V1, the first orange nodes, or V3 or V2. There is no such possibility that those nodes get influenced from the other side. But but this lime colors nodes, which is basically is a common neighbor to V1 and V3. So there is a possibility that this node gets influenced by both V1 and V3, or this node gets both V2 and V1. These nodes may have much there are half distance, but still they can be reachable from V1 and V2. But orange nodes can't. So then we can create one lower approximate region and the upper approximate region. And then what is more important is that lower you can calculate exactly, right? Deterministically expectation. You can calculate the expectation deterministically, but the boundary region, this blue color nodes, where you cannot distinguish, you need to run the Monte Carlo. So once you've done this graph granulations, then you have a smaller graphs. So you can merge those into a super nodes, and that becomes this stage 2, where basically this blue boundaries becomes a super node and the connections becomes your smaller size network. And in that smaller size networks, you can run 10,000 Monte Carlo. But because of the size is smaller, this runs much faster. And here in the stage one, the lower bound, you can exactly count the expectations and do the operations. So this is the main logic behind this particular research. So how to do it? We estimate the diffusion size of the lower approximation based on the total influence, which is expectation calculations of that particular range. And the model is a graph and their expectations, propagation probability presented in lambda. So I'm not going into that details. But what we did, the total influence is giving you the expectations at level 1, the expectation at level 2, and expectations and so on and so forth. So in such a way, we will calculate a jth level expectation value by the formula written. So it's a recursive kinds of algorithm. So you can have a recursive formula of this particular thing. So we can represent that in a recursive formula. So how we did our experiment? We generated two data sets. From one is BA is the Barabasi-Albert algorithm. So we use a Barabasi-Albert algorithm, generated a 500 nodes network, and another is a LDBC datagen package, which is a map-reduce algorithm to generate a distributed network, and we generated there 200 nodes, means 148 nodes network, and we run our experiment. So we compare these algorithms with the traditional Monte Carlo simulation. So the conditions is like this. So if I don't have this particular algorithm, I need to run 10,000 times Monte Carlo simulation. So let's run that and see how it performs. So we did not check with a large scale network because we need to run that, right? 10,000 simulations, and that is a computationally heavy process. So we generate a small network and test it. And then we compare that, what is the execution time we are getting. So what is the benefit we are getting? And then you have to also ensure that the spread size is not too much differs from. Spread size will definitely differ because this process is different, but it should not be too much different, or the ranking between these nodes should not be hampered. So we compare that into these two parameter side. And this is our results, that Monte Carlo simulation, while taking like 1279 seconds for a simulation or identifying 15 nodes out of these BD algorithms, the hybrid simulation giving that result in 1 second. So that's the time gain we are getting. So if you just look into the Barabasi-Albert networks, from 14,447, we are getting it in 11 seconds. So that is the time we are gaining. Now, what about the spread size? The spread size comparison, it's definitely different. It's not exactly same, but it's very close. If you just look into that this giving 7.8, we are having 5.3, and the variance is also for this 10,000 runs. The variance is also almost in the similar line, 10 and 11. Same is true for Barabasi-Albert network. So it's 2.144. We are having 2.152, having a similar variance. So the results remain same. We are gaining 10 folds or 100 folds in a time segment. So that's what we develop. So now it is also important to have a total influence of a set of nodes. So we try to figure out if it is possible to calculate that. And in case of total influence of a set of nodes, you cannot just sum it up, right? Because the influence can be overlapping, and overlapping influence means in a stochastic process, it means a joint probability. You have to have a joint probability identified whether that person is influenced or not. Calculating that many joint probabilities is very difficult. So what we try to have some mathematical constructs that we use some kinds of inequality and try to figure out the upper bound of the total influence for a group of nodes. It's not exact value, but upper bound. So we calculate probability of node, and then we calculate the probability of set of nodes. Now here comes the problems where you need to have a joint probabilities identified. We apply inclusion-exclusion theorem, and then we try to figure out the expected values there, and then total influence is defined by this formula. Then by bound theorem inequality, upper bound of this particular probability is the this given by sum of the probabilities of each node multiplied by the neighborhood size. That is where we get the total number, total influence of a set of nodes. So for this particular work, we provided this hybrid solutions, hybrid simulation model, and then obtain the joint probability by Monte Carlo simulation where the overlapping is happening, not the other sides where you can deterministically calculate the expectation. We calculate that, and this can be used for improving the speed of ICM simulations. Any question? So going to our next work, it's published in transactions, IEEE transactions on competition social systems. In 2018. So here we have a double bounded graph set. It's a mathematical extension of graph set, and we propose tension measure, and then use that for a link prediction problem. So social networks are dynamic. So it's had a evolving nature. I already said that nodes are coming and added to the network, and then possibly some of the nodes may be deleted, some of the links may be deleted, you unfriend a person, and so on and so forth. So this link prediction and link deletion problem is there. What there are studies on that which links are going to be created, newly created, and which links are going to be deleted for these kinds of dynamic network. So what we actually it happens. It's not what we thought of. It's really happens that my network actually gives the psychological or societal positions of money, right? So it's like right now you will find that in my Facebook network there will be many IIT Jodhpur students. I possibly may not know them. Okay, never taught them. But still, if I receive some friend request for them, I usually accept that. So those links are dormant links for me, mostly, majorly. So that's actually my psychological output, right? It's how I perceive my network. It's not like how really active my network is. My active network will be very small. Only maybe I am rarely post anything in Facebook or any such kinds of networks. Although I am working with network sciences. So the person usually gets motivated by the activities within its peer, right? In that case, but if I am not that much active, my influences or maybe also less or something like that. But that psychology actually give you that structure of the network. So how individual relationship works may help understand the dynamics of the network. That is where we try to start this work. Then our intuition is that the psychology of human relationship can be traced back to the structural information without help of any high level information. So high level information means what I share, what I like, what I forwarded, what I posted. That is my behavioral layer, right? But structural layer, yes, those many friends I have. Out of those many, let's say 300 are IIT Jaipur students. Out of those many, I only know 70. So to 200 plus, I don't know them, but still they are in my friendship network. So this is a kinds of means that structural network is actually tracing my behavior without actually looking into the interactions. That is our logic. Now we'll see how that perceives here. So we identify different forces. Now with the structures, we will try to identify the different forces, which is driven by the psychology, acting between two different individuals. Then quantify them, and to quantify them, we also developed one new mathematical framework, double bounded graph set. Then define a tension measure, tension force. It's not psychological tension; it's a force, tension force. Use this tension force, we predicted link in the network. So just coming to the graph set, I talked about graph set in the previous problem also, but I never explained that. So that it was proposed by Paolo, and this graph set has talks about the granules. The granules are the objects you cannot distinguish or differentiate, or you can differently identify. They have in some property set they have the same properties, and if I have that, some of the granules may have a property that I partially belongs to the set we are talking about, and this partially belongs to the set is very nicely represented by the graph set. So it defines two different boundaries. One is lower boundary and another one is upper boundary. Lower boundary talks about those granules who definitely belong to the set. And the upper boundary talks about who are definitely as well as possibly belongs to the set. Now, this possibly belongs to the set creates the boundary region, because upper bound also includes the all the granules in the lower bound. So only the boundary region which has this partial belongingness to the set. Now what we identified that while we are talking about relational data, so in the network science it's all about relational data. Now if a relation will have at least we have a two endpoint, right? Now, if I want to define something about any relationship, there could be a possibility that some granules which are somehow related to the right side, some granules somehow related to the left side, but not with the both. So those are actually, if I go to the traditional graph set, those will be put into the boundary region. Now my boundary region will have two distinct property. One is that something is only right related, something is only left related. So I define that in a double bounded graph set. So it has a left upper bound and a right upper bound. And the lower bound. Lower bound is similar to the original graph set, but the right upper bound and left upper bound defines on top of the relationship. Mathematically, it's something like this, that there is a relationship Q and there is this set of attributes on which defines the granules. And now how granules are belongs to the lower approximation, right upper and left upper. Now what is tension measure? Tension measure is the force which is transmitted through a string or cable, a line, a chain, something like that. So can we consider a social link as a string? That is where our contributions comes, that we consider the social relationship as a string and then try to figure out what are the forces applying through that string. And we call that as a tension force. So tension force is a cumulative force which pulls two individuals towards each other. So if I have a relationship, a string like this, then what is the force that pulling these two together? And how we do that? Let's look into this picture. P and Q is the relationship. See, there is no link between P and Q because That is what we want to understand, that whether they will have a future links or not. But here the blue lines and this, there is orange dots and there is a green dots. So that green dots are my right boundary region of my double boundary graph set, and pink dots are the left region of the left boundary region of my double boundary graph set. And in between these three nodes, the triangle formed green links, these are basically my lower approximation. Now, if I have links between two sides, like from pink to green, that means that is actually a pulling force, right? If my friend is also friends of someone, that means they are connected. That means there is a possibility that me is also will be connected to this particular fellow someday, right? So that's a pulling force. The opposite will happen if my friends are creating in between links, right? They have let's say P have a left side, these pink nodes. Now these blue lines are connecting pink nodes. Now too much links that side will pull me towards that friendship groups. Rather, I'll not find someone else in the outside. So in case I have too many collaborators in IIT Jodhpur, I'll not feel like finding another collaborator from somewhere else. So this depicts this kinds of force. So it's actually pull apart. So it's not a pulling together, it's a pull apart between the P and Q. So we identified four such forces. One is if you have many common neighbors, that is a pulling force. Together you will come closer. If there is a cross connections between these boundary layers, then there is a pulling force. And then there is this negative force. If I have some very strong friendship in my friendship group, so I will not have. So those you can negate. So this is what our tension measures looks like. So it two positive force, two negative force, and the cumulative force is the tension force. Now, how these forces are distributed in a real world network? So we crawl Flickr network, and in there we have like 50,000 plus nodes, and we try to figure out what is the tension measure of all physical links, where the physical links is there. So we found that those links have a very high positive tension measure. So tension value can be negative -1 to +1, and we identified that majority of almost 94% having a positive tension value, where the links is there. And the reciprocal, we try to figure out randomly select some nodes where some edges where we don't have any links, and we also figure out what is the percentage of having a positive value. There we found that only 13%, 14% is positive. Rest are either 0 or negative. So now with these results, what stuck to us is that if there is a positivity where there is no physical links, can you just try that as a identification of the link prediction? So those are the links possibly will form in the future. And if I go back, here also you can see that there are 6% negative value. So physically they have link, but actually they have a negative value. So there is a possibility that in future these links will be deleted from the network. So with this logic, we calculated the same things in positive and negative percentage for 5 different networks, and this results is for that. And that logic, we created our link prediction algorithm that we first, for any pair, we calculate the tension measure. If it is positive, we'll say that there will be a future link. If it is negative, we'll say that there will be a future deletion. And we compare our algorithms with different link prediction algorithms like resource allocation, atomic adder score, preferential attachment score, Jaccard coefficients, and we also compare in terms of effectiveness, accuracy, AUC value, and F1 score. And this is how our results looks like. For effectiveness value, this our tension measure is having very effective as compared to others. Accuracy is also higher, and AUC it's like comparable, it's not higher, and F1 score is also higher. And then execution time, this takes little more time because we need to check all those non-existing links, so it takes a lot of time. But the merit is not only that you can identify links, where merit is that this can also identify which links will be deleted. But although we don't have data set to verify that, hardly we delete our links. Even if we are not talking with those many people, I will not delete unless it's absolutely required. So deleting the data, deleted data is very difficult to identify. You can have an interaction graph, and then that interaction graph you can find the delete data. So yeah, so that's what conclusion is. That tension measure, double bonded object, and prediction. Any question? So now this two work was after my PhD work, but now what I'll be presenting. This is my PhD from my PhD work. It's a fuzzy granular social network. I have 40 minutes left. So fuzzy granular social network, we thought that can we express nodes and its neighborhood in the form of granules, and that is also defined by fuzzy set. Now the question is, first is what is granule? I already covered that it's a clump of object which is indistinguishable based on their similarity or proximity or functionality, whatever they say. So there are some set of properties. By that properties you cannot distinguish. Maybe there are some other properties by which you can distinguish, but with some properties you cannot distinguish. Now the question is, why granules? Why you are thinking about granules? So social network is a collection of relationships, and it's a collective behavior. I started with that, collective behavior. So while there is a very small groups, these actors are closely operating groups, right? So my departments, all faculty working towards the fulfillment of my department's goals, right? So somehow we are operating in the same space where it is very difficult to distinguish between those people. So this resembles the concepts of granules, and we try to model that. And now the question is, why you bring the fuzzy set? Now the relationship has a relationship. It's not a yes/no relationship, right? I may have a friends in Facebook or may have a follower in Twitter, but it's not always yes and no. So it's not always that whatever I share, that person also share. There is a fuzziness. There is a belongingness. There is a conceptual similarity. These are not having very precise boundary. So we thought of using the fuzzy set and give some score of belongingness or membership to each side of the relationship. So they have an ill-defined boundary that needs some mathematical constructs other than simple links. So I thought of using fuzzy sets and that granular theory because that comes naturally to solve these two particular problems, that ill-defined boundary and it's not distinguishable based on some properties. So this is how this is a character club again, and how we created something like this. So we created granules around each node like this, and then we created the granules, and then I'll allocate the fuzzy membership in that granules. So it's represented by a triple where C is the center, B is the nodes, and G is the granules. And then we try to figure out some of the properties. We in our work we use this membership value, but any other fuzzy membership value can be used. It's not restricted. Based on your problems, whatever the problem is, how you perceive the distance, you can have a different distance measure, or you can have a different fuzzy membership. So we also normalize this fuzzy membership based on if I belongs to 4 classes, then my cumulative membership should be 1. That's how we normalize this whole membership values. And then we redefine some of the traditional sensitivity measures which is available for graph theoretic problems or structures. So we define granular degree, which is the cardinality of the granule, the fuzzy set, defining the granules, and cardinality of a fuzzy set is the sum of the membership. So it's equals to sum of the membership. Then we define granular embeddedness which defines how much one link or one link is embedded inside each other. So it's basically the common neighbors in the traditional definitions, and here we have the intersection and the cardinality of that intersection. And for fuzzy sets, it's like cardinality is the minimum of the membership. Intersection is the minimum of the membership. Now we apply this for community detection problems where the overlapping community, we try to detect the overlapping community. So the fuzzy rough community definition comes into picture here. So the problem statement is this: with this knowledge representation, fuzzy granular social network, find out the densely connected groups, which is in other words called communities. And the key idea is that identify the granules which have a higher density, because unless it's a high density area, it's not showing the properties of community, right? So we identified whose degree exceeding some thresholds, that's our parameter, and then merge them if they are nearby. If they are very close to each other, then merge. So we have this rules how we can merge, and then we have this threshold or parameters, how you define the boundary and how much you want to merge together. So define theta code. Theta is our parameter, and which defines the threshold, which is the lowest density we need to have as a granular degree. And then we try to merge those theta codes which are very close by or which are neighbors. And how you define that neighbors? We define that by community reachable codes. And there is 3 different kinds of reachability. One is directly reachable. So you are the neighbors. 2 granules are neighbor. Indirectly, 2 may not be the neighbors, but they are reachable by other neighbors. And then the are connected, which is mostly valuable to the directed networks, where there is a middle element. The first question is, what is neighbor? Because it's a granule, there is no relations, no more edges, it's just a fuzzy set. So we define a neighborhood this way, that a granule is said to be in a neighbor if its center lies in the support set of the other. So it should be at least 50% or around that level is overlapping to each other. It becomes neighborhood granules. And who is directly? If it is neighbor, it's directly reachable. But if it is not neighbor, but it's reachable by some in between granules, then they can be called a reachable as well. And then there is this R connected. So P is reachable from P to R, then Q to R. So you call P and Q are reachable. But here it's no, and it doesn't have any value if the network is undirected. But if it is directed, it's definitely have the value. So once I have that, then we need to define the community. Community will have all those reachable codes which satisfy couple of properties. Because that couple of properties is actually giving the boundary in which boundary you want to work. Means whether you need to include more or less. It should be a very concise community definition. So this condition is that two granules needs to be community reachable, and another one is the normalized embeddedness, granular embeddedness should be greater than 1 by epsilon. That epsilon is another parameter for us in this communication. So theta is our density coefficient. That means if you increase theta, more dense community will identify, number will be less, but density will be higher. If you reduce theta, the community will be more less dense and the size of the community will be higher. It depends upon the problems you want to address. Similarly, epsilon is a coupling coefficient. Higher value of coupling means loosely connected groups get merged into a single community. A lower community may result in more number of communities than actual. So it's like they are not connected, they are not merged together, still considered as a community. Now, because these all granules are fuzzy, then a nodes included in that set is also have a membership values from here to there to here, right? So define a kinds of definition that is called fuzzy graph community, where each node can belongs to any community with certain membership values, and it has a real life meaning. Let's say I belongs to a certain membership to my family, and to certain membership to my department, to certain membership to this institute. So these are definitely membership values. So these communities can be viewed in terms of lower and upper approximation in the graph set. So my granule is rough, boundary is fuzzy. That's why it's called fuzzy graph. So now we'll assign a fuzzy membership to those in the boundary region, and those in the lower region, lower approximate region, they will have the one approximation to mention this unity. So they will definitely belongs to that community. So this looks like something like this. So all these yellow nodes belongs to two community. One community is C1, which is a red. Another community is C2, which is blue. And this yellow are belonging to the boundary region. Hence, they will have a different membership of belonging to C1 and C2. We then define normalized fuzzy Melian information. So what normalized fuzzy Melian information say that given a partition matrix which is fuzzy, what is the similarity or what is the mutual information that we gain by another partition matrix in the fuzzy. So if I have one fuzzy partition matrix, which is basically the true level of my community, and if I get another fuzzy partition matrix, now we want to compare these two. Then we want to see that what is the information gained by this the new things. So if it is having a much more gain, that means they are less similar. So that is defined in this particular definition, and which is used for comparing our algorithms. So higher the value of normalized fuzzy mutual information, larger the similarity. So we have normalized that in that respect. So all proofs are available in the paper. And in ideal case, if they are two are similar, that should be 1, and when they are complementary to each other, that will be 0. So that is normalized in that sense. So we use this for measuring the goodness of our partition generated by the proposed algorithm or any such algorithm with the ground truth. And here is the data. So we again generated LFR benchmark data for community structure. So there is a LFR benchmark data where known communities marked as labeled in that generated data, and then we studied the how our algorithm, where our algorithm fits in. So we use the modularity optimization, centrality based community detections, and overlapping community detection CPM, and then our algorithm. And you can see that once our overlapping fraction of overlapping crosses certain value like 0.3, that this algorithm is providing a better solutions. Before that, it is not, it's comparable or not providing better. So for overlapping communities, this algorithm is more powerful because of this fuzzy definition of the fuzzy boundary. Basically, the communities are usually overlapping, and it's hardly any natural network will have a clear partitions. The initial study was started with the clear partitions, partitionings of networks, but recent studies are mostly overlapping. They consider overlapping boundaries. So we also have these results. And so we have a new knowledge representation. So it's not only the graph. Now we can have a fuzzy groundless social network. And then you can use that for traditional centrality measures or community detection. And we also propose NFMI measure, which can be used to comparing any two fuzzy partition matrix. So that is not only for network science or not only for the community detection problem. So any problems where you get to fuzzy partition matrix, you can compare with this particular mathematical measures. Okay, so last very quickly, I have only 20 minutes or so. So very quickly, I'll go to my last publication. This work is done in collaboration with my postdoc collaborators. So it's my postdoc work. But this is a temporal network where we try to figure out fuzzy relative willingness for exogenous factor. The first question is, what is exogenous influence? So usually we see many posts in our social network, wherever. But there are certain things which are coming from external sources. For example, let's say a post is advertised from IIT Jodhpur. That is actually not available right now in the social network. So one of our colleagues will post that. So that colleague actually bringing some external information to the network. Now, once my colleague posts that, maybe the department head posted a position open in IIT Jodhpur, I'll share. So now my information, me sharing possibly have both the information, maybe offline or also from the network. But someone outside may not have, so they'll share from the inside nodes only. Now we try to figure out, can we identify these kinds of exogenous information? Who is more influenced to that kind of exogenous information? So I could be very less prone to any information that is floated into a newspaper. I'll not share anything. But someone else may be a very active and very, there is a likelihood that he will share a newspaper article every time he saw something, right? There are someone who used to copy some posters from WhatsApp and bring that to Facebook, or Facebook to bring that to WhatsApp, those jokes and memes and anything. So these are externally influenced. That is not available in the network. So how we can identify that? And the more important question is, what will do by identifying that? Is there anything you can solve by identifying that? So that's the whole exercise. That can we identify the future content sharing pattern by looking into this? So suppose some faculty is associated with faculty selections, and he or she floats some faculty selection advertisement every 1 week or so. If I have the willingness to identify, can we identify that in the future also he will bring many news from the outside? So this is how we perceive that if we have measure fuzzy relative willingness, which is greater than 0, that means he will bring something from external and put it into the network. On the other hand, if you look into the right side, so they have if a W equals to 0, so then do not forward anything from exogenous informations. Now the concept of willingness is a kind of a vague. It's not like a yes or no. If I am willing, is it a yes? No, no, right? It's like I could be willing for some news, I could be willing for some news or something. So it's a kind of a fuzzy again. So we bring the fuzzy to solve this and solve the uncertainty arising from these kinds of vague word willing. So define a new problem for quantifying willingness to adopt. So earlier work was only for identifying the source, but here we try to work on the willingness. So it's and define that in a fuzzy methodology. And this is how the work actually happened, the flow of events. So if we have a social stream of posts, whatever we are getting like hashtag or anything, and then we split that into a time slots. And each time slot we calculate the statistics like mean, variance of the distributions. And then we fuzzify that in distributions and define the fuzzy relative willingness. And then we sort that up and get the ranking of the who is more willing or who is less willing. So this is the formula. I am skipping that for the time being. So what we did now, for the experiment, what we did is we have two data sets. We actually did more for this presentation. I only bring two. One is generated network, which is same generated network we use in other work. And another one is real world Twitter data, where we have the post and which time that post is happening by whom. So that data set. And now we need to have a transmission model, right? It could not be the simple ICM, because there is two different things you are sending. One is external. So each link will have two different probability. One is the probability of externally influenced post, and another one is internally influenced post. So we have identified two different probability. One is PE and one is PI. And other things is same as ICM model. So with this synthetic network, we assign the few nodes with 1. So it's bringing the news from the external sources, assigning diffusion probabilities to all the edges, and then simulation. We simulate the information diffusion, and accuracy is measured with this artificially created E equals to 1 with the identified FRW measures. So accuracy is measured where we have willingness is greater than 0 and total number of nodes we incorporated in the network. So 3 different settings we checked how the accuracy behaves with the different parameter space. So globally fixed PE and PI, and then in different simulation we vary PE. Once you fix PI and do variations of PE and the opposite one, and that simulations results, and the 200 simulations was conducted, and that results is something like this. And then the other simulations where PE is varying, where PI is fixed, and then the heat map, how different accuracies being identified. And now we also have the variable PE. So it selected 10 different nodes and put different PE for them, and same for PI, and then we vary the other things, other parameters. So we explored all the parameter space, and this is how this parameter, the number of gateway identified means IG is gateway. We are talking this graph gateway is referred to those having E equals to 1. So percentage identified is by this different experiments is quite high in the above. The average is mostly above 0.5. So we identify quite a bit of nodes from that. And same is with the other parameter. Here also the average is higher than 0.5. In fact, the lowest value is 0.5. So compare this result with the traditional target set selection problems or influence maximization problem, because this particular problem is not studied in the literature. So we compare with degree, which is a classical centrality, degree distribution, which is a diffusion dependent centrality, diffusion degree, which actually proposed by us only in 2013. So we compare with that, then a path-based measure and the content-based measure. And this is how this looks like. And the algorithm, proposed algorithm is by far away above to the other comparing methods, because they are not tuned with these kinds of work, right? So it's not blaming that those algorithms should perform, why they perform slower, because this algorithm, this problem is different. So we also check the effect of different parameters, like effect of A, how different A will have a different results. And finally, we check with the real life data. 75% is used for estimating the parameter, and then 25 for testing. And this is how this node identified, top K in the x-axis, and external influence also post in the test set. And our identified external influence nodes is actually producing higher number of external influence post in the network for the test sets. So it's in conclusion, we have a willingness measure, and which is identify who is more willing to share the content. And yeah, we have developed a new problems called top K content producer problems. So who are the top K nodes who will produce new contents in a social network? So this problem was never studied. So we propose this problem. So that's it. So now we have 12 minutes for question answer.
Sir, there is one question from one of the participants that what tools should a beginner select to get basic understanding?
What tools to be used?
Should a beginner yes sir.
Yeah.
Should a beginner
So,
select to get basic understanding?
Yeah. So basically, I will prefer, or I will ask you to use the network X if you are a programmer. So if you are belongs to computer science, IT, or somehow know programming, some bits and things. So I will recommend use network X for network algorithms and pandas for data manipulations. And if you are not programmer, that means let's say you are from other discipline, but still network algorithms interest you, then there is a different tools like Graphy is one, people use. Then I think cytoscope or something is there for biological network analysis. So there are different tools for different. But if you are a programmer, I will advise to go with Python and NetworkX. They have a lot of inbuilt algorithms, so you can directly use that. Even that is true for non-computer science discipline, because they need those algorithms inbuilt. So they will not write algorithms. So those algorithms is also there, but yeah, learning curve will be little higher.
So one more question has been asked, that how do we approach this subject to undergraduate students and motivate them to do research?
Yeah, so what I do, so I developed one social network analysis course in IIT Jodhpur, and this second time I'm offering this time. So the major thing is that you need to bring the experiments. So keep the theory less and bring the experiments and ask them to develop something out of, or generate their own data, see how that degree distribution is, then ask them to identify communities out of that data. Let's build a network from tweets. Ask them to identify any keywords. Okay, let's say the COVID-19, or let's say the vaccine, Covaxin, or Covishield, or let's say some IPL, or maybe KPL, anything. And then they will bring the tweets, crawl the tweets, and then build the network, and then see how degrees are distributed there, how communities are forming there, how links are connected. So those things. So that will give them a perspective or hands-on experience on network science. And then that will kind of give them the research angles.
Any more questions from the participant? They can unmute themselves and can ask. So please share your PPT with us also.
Yeah, sure. I will upload and I'll give the link, because this is created with HTML.
Okay.
Okay, so I will share the link and maybe a PDF version, but that will not be that good looking.
Okay.
So aspect ratio change, or everything change, right? So usually my slides are available in my website. So that
okay. Okay, sir. Thank you, sir. Thank you so much, sir, for this informative session, and you have given so much of useful insights into this social network analysis. Thank you so much, sir.
Yeah, thank you.
Thank you, sir.
Participants, we will be joining tomorrow again at 9:30 a.m.